visiting us from Concordia University on this snowy day. Just a very brief biography. So I bumped into Yang downtown at a AI summit and hadn't seen him for a while. Thought this would be a great opportunity to invite him to give this seminar for the Center for AI and Society. So Yang's well known in the Canadian computer vision and AI community. He did his PhD at Simon Fraser, and then did a postdoc at University of Illinois Urbana-Champaign, and became a professor in computer science at University of Manitoba, where he was for 10 years, I think, roughly. And then took a leave to become a chief scientist in computer vision at Huawei Canada. That was in Toronto, or
that's in Toronto, but it's a pandemic, so I
remote. Okay, all right. And after that 2-year stint, joined Concordia University in the Department of Computer Science and Software Engineering, I think, where he remains today. Yang is quite well known for his work in computer vision in diverse application areas, including image segmentation, human action recognition, work with Greg Morian after that. But I think has become very interested in the general problem of how do you make AI systems more flexible and adaptive online, which I think is what he's going to talk about today. I think is a problem we all really care about. So very delighted to have you here to tell us about that recent work. Thank you.
Great. Thanks a lot, Jim, for the introduction, also for inviting me here. Yeah, actually, I know a lot of people at York, but this is actually the first time I'm giving a talk here. So yeah, thank you for coming, especially on this snowy day. Okay. So today, my talk is about, the title is Beyond Scaling, Visual Learning via Adaptation. So in this talk, I'm going to put out some more philosophical idea I have been thinking about in the past few years, but also I'm going to have some kind of a technical details. So let's start with, this is the pipeline that everyone is familiar now. So this is how we are building AI models nowadays. Basically, for any problem, you start with, for example, a data set. Then once you have the data set, you can build some, you can throw some machine learning model to it, like a deep neural network. And once the model is learned, you are going to deploy the model to serve the users. So basically, in the traditional AI pipeline, there is a very clear distinction between a training phase and the testing phase, okay? So basically, this part is our training. Here, when I say training, I also include the pre-training that's commonly used in NLP and vision nowadays, okay? So basically, you do maybe a pre-training, then followed by a standard training. Then once the training is done, the model is deployed. So one of the big challenges of the machine learning in general is this kind of a distribution shift problem. So for instance, if your model is built, is trained from images on ImageNet, then the model is unlikely to work well if the test image is very different from the ImageNet dataset. So in order to deal with this kind of a distribution shift, I think the AI community in the past few years has been taking a very brute force approach. So the idea is just to scale up everything. So you create a bigger data set. Hopefully the data sets can cover a very diverse range of possibility. Then because your data set is bigger, then that also means that your model has to be bigger and you have to throw more compute in order to sort of extract the information from a huge amount of data set. So this paradigm has been quite successful in the past, I would say, 10 years. But now I think we have to sort of...
Bob, you can leave that open, I think. Bob?
No, I know.
Okay,
sorry.
Yeah, no problem. Yeah, so but now I think we have to come to the realization that this scaling law that has been driving a lot of the AI progress in the past few years might come to an end, okay? So this is the talk from NeurIPS last year. So this is the test time paper award from Ilya. And in his talk, he's mentioning that at least for the LLM scaling, it seems like we are coming to the scaling law is coming to an end because we have run out of the data that's available for doing this kind of LLM pre-training. So another challenge that we have to think about is even if the scaling now is not slowing down, we have to, for a lot of AI applications, quite often the model has to be deployed on some edge device. So in that case, you cannot really just train a huge model, then put the model online, then rely on the API to call the AI model. Instead, the model itself has to be directly deployed on some device because of privacy reason or latency reason or many other reasons. Okay. So, and also for a lot of this kind of application where the AI model is deployed on edge device, quite often the model doesn't really need to handle all the possibility in the world. Quite often they only need to handle a very small subset of our world. So for instance, if you are deploying the model on a robot and you put a robot in your home, all you care about is how well the robot is operating in your own home, how well it's recognizing the people, the objects in your own home. Okay, you don't really care how well it recognizes image from other people's home. Okay, I think this is something that a lot of the AI models nowadays are not taking into account. So the question I want to pose is then, like, other than this kind of just a brute force scaling law, is there something we are missing in the current development of AI technology? So in order to answer that question, I want to sort of take some inspiration from the human intelligence. So basically, when we think about how humans do learning, actually there are two levels of sort of learning related to the human intelligence. One is this kind of learning at the individual level. So like for a particular person, the person might be learn how to drive or maybe learn a certain subject. Okay. So for this kind of human learning, then I think a lot of ideas have been implemented in the machine intelligence as well. So things like self-supervised learning, reinforced learning, continual learning, and so on and so forth. I think for the human learning of this level, our AI community has sort of taking advantage of the inspiration quite well. But I would argue that there is another level of human intelligence that's learning at the entire population or the societal level. At this level, I think a lot of idea hasn't been really taken advantage by the AI community. So for the learning at this population level, the technique that we are using are things like reproduction, evolution, natural selection, and these concepts are not that popular in the machine learning community right now. Okay. So another thing to notice is that at these two different learning levels, the outcome are slightly different. So at the individual level, the outcome of the learning is a very specific model to achieve a certain task. Like for example, if I'm learning to drive, then at the end of the learning process, you get the skill of how to drive. Okay. So, but at the level of the population, the outcome of the learning is not a specific skill or specific to solve some specific task. Instead, you can think about it as essentially a meta model that enables learning at the individual level. Okay, so more concretely, you can think about the outcome of this level of learning is the human genes. Okay, once we have this kind of genes, then the individual human can sort of quickly do the learning at the individual level for some specific task. Okay, so one thing to notice is that. So the outcome of the learning at the population level actually is going to determine how well the learning at the individual level is going to perform. Okay, so because I think like a lot of the machine learning effort has been focusing on this part, but implicitly what you can learn, in fact, is also in some sense constrained by what you got at the population level. Okay, so for instance, because the nature doesn't give us the gene to learn to fly, so no matter how hard you try at the individual level, you are probably not going to learn how to fly. Okay, so I think in order to really unleash the power of intelligence, we need to think about the learning algorithm at these two different levels. So then if we take the inspiration of the human intelligence, so here is how I compare human intelligence with the machine intelligence. So right now, I think a lot of the AI development is focusing on just learning one single fixed model, and once the model is learned, you deploy the same model everywhere. But instead, if we take this inspiration from the human intelligence, maybe what should be learning is that we should be learning some kind of initial model, just like a human evolution gave us. Then once that level of learning is done, then the learning can keep continuing at the individual level. So basically, an individual person can keep learning certain skills that are important for that particular individual in the particular environment. So then at a philosophical level, philosophical sort of a perspective, I think that the human intelligence has a lot of advantage compared with what we have in the AI community. So, for example, let's take a thought experiment. So let's imagine that through millions of years evolution, all the experience of all the humans on the planet are somehow digitized. Okay, then the nature has a chance to create an entirely new species. Okay, so then what kind of species would the nature create? Okay, so one possibility is the nature might create something like the human nowadays. So you create a human, then the human has this capability of adaptation and continual learning. But the other extreme is maybe you can create a species that are sort of just has a huge amount of intelligence. This is basically like how the LLM is doing nowadays. Okay, you basically take all the experience of all the humans, then create a very big sort of a creature that has all the intelligence in the world. But that creature may not have enough capability to adapt and to continue learn. Okay, so then the question is, which of the species is more likely to survive? Okay, I'm going to argue that actually the human way is more sort of likely to survive, because if you because if you create a creature that are really intelligent, but it's basically that creature need to have maybe have a very big brain. Okay, just from the biological point of view, that means that creature need to consume a lot of energy and the nutrition. Okay, and if that creature does not have enough capability to adapt, if there is some kind of environmental change on the Earth, then that creature might likely to extinct very quickly. Right? So basically, I think this kind of a human evolution gives us a very robust way to handle this kind of a change in the environment and allow us to be more robust to unexpected situations. And also, it's a more sort of I would argue it's a better way of using resource. Okay, so because for our brain, the brain is always going to consume energy and nutrition. Okay, so if so, you might ask why wouldn't the evolution give us a bigger and bigger brain? Okay, so if you look at the human brain, it's not that much bigger through the evolution. Okay, so I think that there is a reason for that, because for example, if you have a very big brain, then that's going to consume a lot of sort of resource. Okay, so but maybe for a particular individual to survive in a particular environment, it doesn't really need to handle so much sort of situations in some sense. Okay, so maybe the physical sort of size of our current brain is enough. Okay. All right. So then I also sort of want to sort of contrast this with So basically, I think in machine learning, we are a little bit too obsessed with this concept of generalization. We want to build models that are just work out of the box all the time, regardless of what the situation is. Okay, but if you look at how humans construct our society, that's not how we do things. Okay, so you really don't find any humans that are sort of have the skill to do every single job in the world. Instead, humans have to specialize to a particular function in the society. So some of them might become engineers, some might become teachers, some might become doctors, and so on and so forth. So basically, every individual has to specialize in order to function well in our society. Okay. And also, if you look at the tools that we have building in our society, we often don't build the tools that can do every single thing. Okay. Instead, we build the tools, for example, for different tasks, we build very specialized tools. Even for one single tool, we often build a different version of that single tool to fit to different use cases. For example, if you think about the computer, so this is a tool that we use all the time. But for different use cases, you actually build the computer slightly differently. For computer use in the data center, it looks very different from the computer that you use at your laptop. Okay, because these two different scenarios call for different attributes. All right, so then basically the idea I want to propose is that instead of just building one single model that fits every scenario, how about we build a model so that the model has this capability to adapt and continue to learn after it's being deployed. So this basically is taking the inspiration from the human intelligence. Okay. All right, so now I'm going to present several concrete projects we have been doing in the past few years. In fact, we have been working on this idea a lot. We have used it in many different applications, but because I only have about an hour, so I'm only going to present this few pieces of work because I think this work represents several different distinctive techniques. Okay. So let's start from the first work here. I'm going to use the point cloud registration as the application, as an example application, but the technique can actually be applied in many different areas as well. So I'm sure many of you know this point cloud registration problem. So the problem is given two point cloud. We want to estimate the parameter so that we can align these two point cloud together. Basically, you want to estimate this kind of like a translation or maybe rotation so that you relate these two point cloud together. Okay. So then this is a very classic sort of a machine learning problem. So imagine that on your training data you have these kind of pairs of point clouds, then you have a ground truth that give you the parameter that relate to this two point cloud. You can easily build a neural network so that the neural network take a two point cloud, then output this kind of a transformation matrix. Okay. So then basically this is what most of the previous work is doing. So basically the previous work just treat this as a purely supervised approach, then learn the parameter in the neural network through this kind of a standard supervised learning. Okay. So, but the limitation of this is that if you use this kind of a purely supervised approach, the model is fixed once it's trained. It's not going to adapt to any new input during testing. So in our work, what we want to do is, the high-level idea is we want to have this capability so that the model can actually adapt itself once it sees a particular test instance. So the way we do that is we design our model so that basically, like given the input, we have a shared backbone network. This network is going to extract the feature representation. Then from the backbone, we are going to attach two different branches here. So for the first branch, it's going to so in fact this technique is called test time training. We are not the first one to propose this. So this is actually already available in the literature. Okay. So like for example, if you are doing image classification, then maybe the first the primary task is just the class label. In addition to the primary task, you also attach a so-called auxiliary task. And this auxiliary task is going to provide some kind of a loss function during testing that allow you to do adaptation during the testing. Okay. So for instance, during for image classification, you can consider this kind of image rotation as a auxiliary task. Okay. All right. So then we in this work we are going to use the similar idea for the point cloud registration. So here our primary task is going to output the transformation matrix that are related to input point cloud. And for the auxiliary task, we are going to define several auxiliary, several self-supervised auxiliary tasks in this branch over here. Then once you have this kind of architecture during testing, because this auxiliary branch is going to provide some loss function, so through this loss function you can do a few gradient update. Then this gradient update is going to change your change the parameter in the backbone. Then you use the updated backbone together with the primary branch to output the final output. Okay. All right, so now let's look at some of the detail here. So in this work, we instead of having one self-supervised task, we actually use several self-supervised tasks. So the detail doesn't matter too much. In fact, you can, if you have any other of your own favorite self-supervised tasks, you can just directly plug in into the model. Okay. So in our work, so this is the first self-supervised task we use. So basically, we are just using a point cloud reconstruction as a self-supervised task. Okay. So it's self-supervised because during testing, you don't need any human annotated label to define the loss, because it's a reconstruction. So you can just use the original input to define the loss. So for the second self-supervised task, we use a idea from the self-supervised learning literature. So it's called a BYOL. So it's the detail doesn't matter too much. Basically, the BYOL algorithm just give you a self-supervised loss that allow you to do feature learning. Okay. So we take the idea there and we just use this as our second self-supervised task. So for the second self-supervised task, we consider this correspondent classification. So the idea is you are given a point cloud, then you just maybe rotate the point cloud by a certain degree. And because you know the rotation, then you actually know which point cloud, which point in the first point cloud corresponds which point in the second point cloud. Okay, so then you can define this kind of a correspondent classification. This will give you a self-supervised loss.
Sorry, could you just go back
Yeah.
to the second loss? What was the radial loss?
So this is a standard. Basically, this is a standard self-supervised learning algorithm that people use for example, for just learning the feature representations. Okay.
Okay.
Here we just directly take that and use it. So because when we were doing this work, this BYOR is perhaps one of the best at that time. But if I'm doing the project now, I'll probably use some even better self-supervised learning, maybe master autoencoder. Okay, but the detail doesn't really matter because you can take any algorithm from the self-supervised learning literature and that can be used here.
But here it says predicting an augmented view, so it's similar to the rotation.
Yeah, it's in some sense, like at high level, it's similar. Yeah. All right, so another detail here is that here we have defined 3 different self-supervised laws. Then we need to have some way to combine them together. Of course, you can just for the weight over here, you can set it manually. But in our work, we actually treat the weight as another learnable parameter. So we let the algorithm to figure out which self-supervised learning laws contribute more to your final task. Okay. All right, so then once you have this kind of a setup, you are going to the naive way of training the model parameter is you just treat it as a multitask learning problem, and you have 2 laws here, one loss coming from the primary branch, another loss coming from the auxiliary branch. Then you just learn everything together. But the problem of the learning parameter in this way is that, depending on how you set up your hyperparameter, your model might focus on the auxiliary task rather than focusing on the primary task, which is something that you don't really want, okay? Because the final goal is you want to do well on the primary task, okay? But if you train your model parameter this way, it's not specifically trained to perform well in the primary task. So in order to solve this limitation, what we are going to do here is we use a meta-learning approach so that we train the model parameter in a very specific way so that the model is trained to perform this adaptation well during testing. Okay. So here is the idea of this meta training. So basically during training, in every iteration, we are going to sample a training instance. So then we pass the training instance into our network, and we get the feature vector. Then we pass it to the auxiliary branch. Okay. So the auxiliary branch is going to give us some loss. Then we know that during testing we are going to use this loss to update the model parameter. Okay. So then basically during this kind of a meta training, we are going to simulate what will happen during testing. Okay. So basically, we know that during testing we are using this loss to update the model parameter. Then during this meta training process, we are just simulate this whole process so that we update the model parameter according to the self-supervised loss. So we get this updated model parameter. Then we use this updated parameter to perform this prediction in the primary branch. So the primary branch is going to predict this kind of a transformation matrix, which is the final output we want. Okay. But remember, this is during training, so that means we also have the ground truth. Like a transformation matrix for this primary branch. So that means we can actually compare this loss in the primary branch, because remember this is training, so we do have the ground truth. So then that means we can update the model parameter in the outer loop. So basically the meta training algorithm is going to have the inner loop, then it's going to have the outer loop. So in the inner loop, basically the algorithm is just simulating what's going to happen during testing. Then in the outer loop, you are just using the true ground truth label to supervise the whole learning process so that the adaptation during the inner loop is giving you a good result so that you can use to perform the task in the outer loop, in the primary branch. Okay. So the advantage of learning the parameter in this way is that now the parameters are learned in a very specific way, so that during testing, if you update the parameter using this updated rule in the inner loop, then it's gonna perform well in this outer loop. Okay. All right. So then once the model is trained during testing, then it's very straightforward. Basically, during testing, you are given some test image, but now you don't have ground truth anymore. Then what you do is you pass the input to this auxiliary branch, then update the model parameter using the loss provided by the auxiliary branch, then use the updated model to perform the prediction in the primary branch. That will be the final prediction. Okay.
Excellent.
Yeah.
I actually didn't figure out completely what's the difference between the test time training and the beta learning. And the test time training, you have an auxiliary branch and an auxiliary loss during the training, and you use the auxiliary loss during the test too, in order to update the parameters during the test time to adapt to the output of the distribution data, right?
Right.
But what about the...
Right. So in the literature, you might see a lot of paper called test time adaptation, but usually those paper, what they mean is, for example, you train your model this way. Okay, you just train it as a multitask learning problem. Then during testing, you update the model using the auxiliary branch, then use the updated model to perform the prediction. So during testing, that's exactly the same as what I described. The key difference is during training, because if you do this, if you learn your model parameter this way, the model are not learning the model parameter has no idea that during testing you are going to do this adaptation step. Okay, but if you use this kind of meta training approach, so basically during the meta training, you are learning your model parameter in such a way that it's ready to do adaptation during testing using the auxiliary branch. Okay, that's the key difference. Okay, yeah.
So even when you've got this double loop to optimize the way that it's learning to adapt, at test time, because you only have the auxiliary loss, what prevents, you know, in the limit, what prevents the network from degenerating?
Right.
Do you still need to have a stopping criterion?
So from the implementation point of view, so when you are doing, like for example, when you do this kind of adaptation, usually you don't want to adapt too many iterations because you only have one instance. So typically this is the hyperparameter you have to choose. So usually you only do maybe 1 to 5 update. Okay. So, but to answer your question of what's preventing the model from just go crazy during testing, so this is the same argument of why traditional machine learning doesn't go crazy. Okay. So the reason that like if you think about that, you train a machine learning model, the reason that you remember that the data you see during testing are not what the data you see during training, but you still have some confidence that if I'm doing well, reasonably well in training, I shouldn't be too bad on testing. Okay, so it's the same idea here. So because during the traditional machine learning, you have supervision during training. Okay, so basically you know that if I'm doing well on my training data, I should be reasonably doing well on my testing. Right. It's the same thing here, because during training you have an outer loop supervision, which is the true supervision. So you have this supervision during training so that you know if I'm updating my model using the auxiliary task, at least during training I see, oh, my model is doing reasonably well. So then you should have reasonable confidence that during testing, if I do the same thing, it should be performing okay at all. Okay. So that's a sort of a basically it's a generalization of the traditional machine learning.
But you still don't have any anchoring supervised loss. So I think, as you said earlier, if you just, no matter how good your learning algorithm is, if it's just got the auxiliary loss at test time, if you didn't have that stopping criterion, wouldn't it ultimately degenerate?
During test time, when you do the update, you just like if, for example, during training, if the update in the in loop, you only take 1 to 5 gradient update. Yeah. During testing, you are going to do the same thing. Yeah, so that's how you can make sure that it's not going too crazy. Yeah, go ahead.
So I'm just asking one of these naive questions because I'm not in computer vision, but like for example, many cases people when they're trying to improve the robustness of the vision model, in the training data they always augment with this kind of synthetic kind of augmented. In this case you rotate, right? But other people can do kind of reducing the resolution or adding forks to it and so on, right? And then just train the model as a result with this bigger data set. Did you compare how effective this approach with that kind of?
We didn't compare that, but I think that like doing this augmentation is orthogonal to what I present here. For example, you can just augment your data, do some augmentation and do the same thing here. So these two things are orthogonal to each other. Okay, but I think the issue of augmentation is that it implicitly assumes that you already know what kind of noise you are going to encounter during testing. Like for example, in augmentation, quite often you just rotate the image a little bit, or maybe change the do a little color jittering a little bit. So implicitly you are saying, oh, during testing, that's the kind of variation I'm going to encounter. But that's not always true. Okay, so that's a limitation of just doing simple augmentation. Yeah.
So in this case, just a follow-up. So later on, like in this round, you think, you know, one way is rotating the image, but later on maybe you realize there's another way to perturb the realistic setup. You can do another round and update. Is that the way, or it's just one round?
Well, here we are just having one round, but towards the end, for the third part, I'm going to talk about some other things that involve maybe multiple rounds of doing things. Okay.
Okay.
All right, so then we compared with some other approach. So basically, we use the nice thing is this whole framework is very general. You can use it on top of any point cloud registration network. Okay, so here we tried 3 different backbone, and we just add our approach on top of those backbone, and we show that it improved the result. Okay. All right, so now I'm going to move on to the second work. I call it the test time domain adaptation. Okay, so this is here I'm going to present the 2 paper, but the second one I'm going to present very briefly. Okay, so the motivation for this work is that we all know that in computer vision and in machine learning in general, there is this kind of domain shift problem. So if your data are coming from several domains and you use those data for training, quite often if you use it in a different domain, the performance is going to drop significantly. Okay, so we want to sort of address this kind of domain shift problem. So in particular, let me give you the background on one of the applications that we use in the dataset. So in this dataset, so this is collected for wildlife monitoring. So people set up this kind of camera in different places and record the animal behavior, and they want to recognize those animals. Okay, so then you can imagine each of the camera is one domain because that camera is set at a particular location at a particular angle. So then you can imagine that for the image captured by a particular camera, it usually has some very special characteristic because it's at a particular location with a particular angle and so on and so forth. Okay, so then let's imagine that during of course, like the naive way of solving this problem is you just collect all the image from all the training camera and train one single model. But as I mentioned before, this is perhaps not the best way of doing things because every camera has their own characteristic. So instead of what we want to do is we want to build a personalized model for every camera. So now let's imagine that during training you have training images collected from multiple cameras. Then during testing, maybe you are given a new camera. Then we assume that you have a very small amount of unlabeled images from that new camera. Okay, so because it's very unrealistic to assume that you are going to have people to label the images from the new camera. Okay, so for the target camera, we are going to assume you only have a very small amount of unlabeled images. And from there, what we want to do is we want to quickly create a new model that are specifically tuned for this new camera in a very sort of efficient way. Okay, so this is our problem setup. So once you have this model, then once like if you have new images coming in this target camera, our model is going to perform inference on those new images. All right. So in this paper, we are using this idea of a mixture of expert. So in fact, one of the motivation for this work is that we want to take advantage of this kind of decentralized and privacy preserving kind of a property. So here what we are going to do is we treat every training domain as an expert. Then for each of the experts, it can train a single model using the images from that expert. So in the end, we end up with multiple experts. So then what we are going to do is for a new target camera, we are going to sort of so basically we want to aggregate the knowledge that coming from these multiple experts in a way and transfer the knowledge to this new target camera. So the way we are going to aggregate the knowledge from multiple experts is that we learn the aggregate function. So remember we have, let's say maybe you have 100 experts here. Then we are going to learn the aggregate function so that essentially it's just combine the knowledge of these 100 experts. So once you have this combined knowledge from different experts, we just perform a distillation step so that we distill the knowledge from this kind of a combination of the multiple experts into one single model. Because it's like in practice, it's not very convenient to have a mixture of experts as the final deployed model because the computation is too big. Okay, so in the end we still want to have one single model in the end to deploy to the target camera. And the way we do that is through this distillation, we can create the final model we deploy. So then another question is, so in this whole framework here, we have two modules that have some learnable parameter. We have to figure out how to learn them. One set of parameter is just in this aggregator function. Okay, so basically how to aggregate the information from the mixture of experts. Another set of parameter is this kind of the parameter in this smaller network. So in fact, this is the initial parameter in this smaller network. So once we have these two parameters, during testing, we can just use the distillation loss and update the parameter here a little bit. Then this will be our final deployed model. So now the question is how we learn the parameter in these two blue box here. All right. So then we are going to use a similar techniques that I have presented in the first work. So basically during training, remember during training we do have the ground truth images for any training domain. Okay. So then what we are going to do is we are going to use the training image to simulate what's going to happen during testing. Okay. So then the way we do that is maybe during a particular iteration, we are going to sample one of the domain from the training domain because this is going to simulate what happens during testing. Okay. Then once we have a sampled domain, then we are going to pick some small amount of the unlabeled image from that sampled training domain. We call it the support set. Then we just pretend these are unlabeled images. Okay, even though they are technically training image. Okay. Then we pass the support set into this network over here, and remember, so then this will be our inner loop as I showed before. So basically in the inner loop, we update the model a little bit based on the support set. Then remember, this is the training. So that means for that sample training domain, we also have other images that are labeled. So then we are going to call that a query set. So the image in the query set, we do have the ground truth here, okay? So then what we are going to do is we take the updated model parameter and pass the query set into the updated parameter to make a prediction, then compare it with the ground truth label on the query set. As I mentioned, for the query set, we do have the ground truth label, okay? So this is going to provide a supervision signal in our outer loop. So again, we have this kind of a two-level optimization, and the model parameter in this two box are learned in a very specific way, so they are ready to adapt to a new camera during testing. Okay.
Sorry, what's the task?
So the task is during testing you are given a new target domain, a new camera. Then you have a very small amount of unlabeled image from that target camera. Then you want to quickly create a new model that are tuned to that target.
No, but is it animal?
Yeah, it's just animal classification task. Yeah. Yeah, so this is the data set that we use. So like this data set has many different tasks. Like for example, one of the tasks is monitoring animal. Another task is this kind of a medical image classification. So you can imagine different lab or different domain in this case. Okay. All right. So then so here are some quantitative results. So we show that doing this kind of adaptation give you. Yeah.
So you mentioned in the last method, there's kind of optimization during test time and during training time.
Yeah.
Test time and training time.
Yeah.
Is that the same case here where?
Yes. Because here during testing, during testing, you are given a new target domain. Then you are given a few unlabeled image of that target domain. So based on that a few unlabeled image, you first do this adaptation step, which is here. Okay. So once the adaptation is done, you have an adapted model. Then at this stage, if you have new data, new image coming in, then you use the adapted model to do the inference. Okay. So basically, in this case here, this adaptation is only done per domain, not per instance. Okay. But in the first work I showed, the adaptation is done per instance. Okay.
So in the test time, what is the loss?
So you mean the loss for doing adaptation?
Yeah.
So it's the same distillation loss. Okay,
Right.
it's just like in the meta training stage. Okay.
Okay.
All right. So then let me just for this paper, I'm just going to quickly go through it without getting too much into the detail. So for this paper, it's solving exactly the same problem, but instead of using a mixture of experts, we are using a foundation model because at that time the foundation model is just getting popular in computer vision. So we thought, oh, why don't we just do a version using the foundation model? Okay. So basically here we are doing exactly the same thing. The only difference here is that this adaptation is achieved through this kind of a prompt engineering approach. So basically what we do is given a domain, we learn a function that map from a few unlabeled image into a domain specific prompt. Okay, then this prompt is going to allow you to steer the foundation model to perform well on a particular domain. Okay. I'm going to skip the detail, but if you're interested, I'm happy to talk offline. Okay. All right. So then, finally, let me just quickly present another work on continual. This is we call it a continual category discovery. Okay. So here the idea is that so far we have been talking about adaptation only involve adapting once. Okay. But there are many application scenarios. Maybe you want to sort of your data is coming in a streaming fashion, and you want to keep adapting your model to the unexpected new scenario. Okay, so in particular, the problem that we look at in this paper is this idea of discovering novel classes. So one of the limitations of standard image classification is that it assumes that, for example, if you train your model to recognize 1,000 category, it can only recognize 1,000 category during testing. But in reality, quite often during the test time, you might have images of other category coming in. Okay, so we want to have a way to somehow also being able to handle those new categories that you never see during training. Okay. So then we propose this problem called continual generalized category discovery. So the idea is we assume that first you have a offline training stage. So in the offline training, maybe you have a label data set. Maybe your label data set has, let's say, 1,000 category. Okay. Then of course from that you can learn the model to recognize the 1,000 category. Then the model is deployed in the real world. And in the real world, the data is coming in a streaming fashion. So at each time step, you are given some unlabeled images. So those unlabeled images might contain objects that you have seen before, or it may contain some new objects that you've never seen before. So perhaps maybe in the first time step, you are given some unlabeled image that contain 5 new objects. So then the goal is we want to discover those 5 new object category and build a model on it. Okay. So then that means at the end of the first session, then we are supposed to recognize the 1,000 plus 5 category. Okay. Then in the next time step, maybe you are given another new category. Then we want to sort of recognize 1,000 plus 5 at the end of the second time step. Okay. So basically, we want the model to have this capability of incrementally increasing its capability of recognizing more and more category. All right, so then so then basically what we want to do is, remember I mentioned before, we have an offline training stage. So of course the naive way is during the offline training, you just train your model using the standard supervised approach. Then you learn the model, then maybe during testing you just use the learned model as a feature extractor, then have all kinds of ad hoc things during testing. Okay, so that's one approach. But the disadvantage is that then the model during offline training, it doesn't know its own purpose in the end, because it's learned to recognize those own 1,000 category. It doesn't know that during testing you are going to use it in a different way. Okay, so here what we want to do is we want to sort of learn basically during offline training, we want to learn the model in a specific way so that it's ready to adapt during testing. Okay. So let me first set up some basics before I describe the algorithm itself. So here we are going to first propose a learning object that's unsupervised. Because remember, during testing, the images are all unlabeled. There is no human supervision. So you have to rely on some unsupervised learning objective to update the model. So the technical detail doesn't matter too much. Basically, we just use a contrastive sort of loss to add our unsupervised loss function. Okay. Oops. So then we can also define a supervised version of the contrastive learning. So for this loss over here, we do have a component that requires supervision. Okay. So this is what we are going to use during the offline training, because during offline we do have the ground truth. Okay. So then, during the offline training, what we are going to do is we are going to remember during testing. What we are going to do is we have a model, then the new data coming in, then we have to somehow update the model based on the unsupervised loss, then do the novel class discovery. Okay. So then during the offline training, we are going to use our training data to simulate this entire process. Okay. So for example, let's say if you are using this CFAR dataset during offline training, maybe you have 80 classes. Then we are going to use this 80 classes to simulate this entire continual learning process. Okay. So then the way we do that is in every episode, we are going to from those 80 classes, we sample maybe 60 as a pseudo base label. Okay. So this is going to simulate the fact that you have this kind of a base learning first. Okay. So basically here in this particular episode, maybe we sample 60 of them as a pseudo base label. We learn a model here first. Then we use the remaining 20 class to simulate this kind of a continual learning process. Okay. So for example, we can split the remaining 20 classes into several time steps, and in each time step we add 5 new classes to it. Okay. Then for the first time step over here, we have 5 new classes. Then we use the unsupervised loss to update our model. But remember, this is during training, so that means we do have a ground truth as well. So then we can have so in the outer loop, we can also define a true sort of a supervision signal that allows us to simulate this whole process. Okay.
So in the offline learning, are you using the contrastive loss on all categories or just the unlabeled categories?
Right. So maybe let me oops. Oops. Sorry. Yeah, so maybe this slide will be clear. So this diagram just shows what happens during this kind of during one episode of this meta training. So in one episode, we sample maybe 60 of them as a pseudo class. Then we use the remaining one and we sort of put them into this kind of a sequential kind of ordering. Okay. Then we are going to have the inner loop and the outer loop just like before. So in the inner loop, we for every time step we take some unlabeled image from those 5 new for that time step. It could contain maybe 5 new categories, but it can also contain images from the previous category you have seen before. Okay? So then what we do is in this time step we use the unsupervised learning objective to update our model. And in the next time step, again, we use the unsupervised learning objective, but only use the image in the second time step, and we just keep updating it. Okay. Then at the end, we also pass other labeled image to the model to have a ground truth supervision signal. Because remember, this is the offline training, so we do have the ground truth. So we use this kind of a pseudo test image to provide the supervision signal in the outer loop to supervise our model to learn exactly how to do this kind of continual learning. Okay.
Yeah, but it's not being told that there's 5 unknown categories in this case. It's just
right. So in this paper, we the 5 is the magic number you have to set. So in this paper, we assume you actually do know that, but of course that's the limitation of this approach. Okay. In fact, that's the limitation of all approach in this topic. Okay. But basically, yeah.
If it's just a contrastive loss, why do you need to tell it how many unknown categories?
Right. So in fact, you let's see. Yeah, so in the end, our model just learn essentially it's learning just a backbone. In fact, it's just learning a feature extractor. Then you can run the k-mean algorithm on top of that backbone. So the file is just chosen, from our algorithm point of view, we don't need to know that magic number of 5. But for evaluation purpose, you do. Because for evaluation, you need to somehow match it to the ground truth. Yeah.
Yeah. Yeah.
Yeah, so I have a question.
Yeah.
So, I have some issue with this kind of labels. So I noticed some of these labels are quite general, right? Some of them are very specific. Like, for example, for fish, you have something called crawfish instead of just fish. But for fox, you just say fox instead of saying red fox, Arctic fox. And so, how do you know if an image is uncategorized or just doesn't belong to, let's say, smaller category but the bigger one? Like, I'm just unclear about this part.
Right, that's good. That's a very good point. So I think one implicit assumption we are making is the granularity of the object at the offline training match the granularity of the object you see during testing. Okay, so if on the training data you are only seeing this kind of a course level object, you wouldn't expect the model to be able to recognize a very fine detailed object during testing. Okay, so that's our implicit assumption. So for example, the data set we are using, like the CFAR data set, in general, all the objects are roughly speaking at the same sort of granularity. Okay, but if, for example, if you use CFAR as the offline training, then suddenly during testing you are giving it a very detailed, like a fine-grained category. I wouldn't expect the algorithm to work that well. Okay. All right, so then here are some numerical numbers. You can see that like we outperformed the previous approach. So this idea of learning specifically to learn seems to work quite well. Okay. All right, so finally, I want to sort of I want to connect what I have presented so far to some other topics that are very popular nowadays, not just in computer vision, but also in, for example, natural language processing. Okay. So in NLP, I'm sure everybody knows this kind of idea of LLM is very popular nowadays. And in the LLM world, one of the techniques that have been very popular recently is this idea of inference time computation. Particularly if you want to use LLM to perform some very complex reasoning tasks, quite often you have to spend more time doing inference. Okay. So things like OpenAI O1 or the DeepSeek R1, those are the example of this kind of inference time computation. Okay, so in some sense you can interpret what I have been talking so far as a form of inference time computation or inference time algorithm. Okay, but the difference is the algorithm I have been presenting involve updating the model parameter itself, but the inference time computation that coming from the LLM world usually does not involve updating the LLM parameter. Okay, but I think this is perhaps more of a technical issue. So because for a lot of LLM, it's not even open source, so you don't really have access to the weight. Or even if you have access to weight, the model is too big, so you cannot really do update anyway. But fundamentally, I don't think there is any fundamental reason why you couldn't do inference time computation involving updating the model itself. So another sort of a very popular topic nowadays is kind of embodied AI. So the embodied AI just means that during testing, you allow your agent to perform certain actions rather than just passively processing the incoming information. So in some sense, you can interpret this idea of updating the model as one example of performing the action, because the agent is deciding, oh, I'm going to use this loss function to update myself a little bit. Okay. So another very popular topic nowadays in the literature is called the agent. Okay, but nowadays when people say agent, usually they mean LLM-based agent. Okay, so usually those agents can have basically, like, for example, use advanced tools, or maybe like you can have multiple agents collaborating with each other. Okay. So in a very general sense, you can also interpret this idea of updating the model as an example of the action that the agent can perform. So the agent can decide, oh, I'm going to call this tool, or you can decide I'm going to update my own parameter a little bit. Okay. So I think that this idea fits quite well in a more general framework. Okay. So finally, I want to sort of connect to this quote from the beta lesson of Rich Sutton. So in this, I'm sure this is something that a lot of people know about. So, but a lot of people, when they see this beta lesson, they interpret it as just throwing more GPU into your problem. Okay, but I want to interpret this in a more sort of a broader sense. Okay. So in the beta lesson, basically it says that we also, in addition to learning, we also have to rely on search. Okay, so search often means that you have like for example, like a discrete algorithm or maybe optimization. These are examples of the search. Okay, in fact, updating the model according to some loss function, you can interpret it as a form of search as well. Okay, so then also I want to sort of interpret this learning as not just the traditional learning that we are familiar with. Okay, so this kind of offline learning, to me that's just one form of learning. After the model is deployed, the model can sort of continually update itself and continue to learn. To me, that should be part of the learning as well. But I think this is something that hasn't been explored too much in the literature yet. So finally, I want to sort of interpret this computation in a more broader way, okay? Because nowadays, when people say computation, they just mean the GPU server that you use during the offline training, okay? But nowadays, for a lot of model, when you deploy, like say you deploy it on the cell phone, nowadays our cell phone has pretty good computation power as well, okay? So now, but currently we are only using the cell phone as a sort of an inference machine. But you can imagine that if we can allow the model to adapt and to continue to learn, this is going to take a better advantage of the computation power that people have on their cell phone. Okay, so I think if we can have AI system that sort of can take advantage of all the computation, not just the GPU server, this is going to sort of help us to democratize the AI technology. So one thing I really hate about the current AI paradigm is the power is too concentrated on just a few big players. What I like to see is, in the end, every single person, even with their own cell phone, they can contribute to the learning of AI model and the advancement of the technology. And that's all I have. And thank you for your attention. I'm happy to take any questions.
Thank you so much for a great presentation.
Thank you.
So, correct me if I'm wrong, but I think in the techniques that you mentioned, most of them, for example, test map training or beta learning, we are changing the loss function during the training of the main model. So, suppose that we have a model which has been trained during the deployment, and we don't want to retrain the model during the training to change the loss function. We have only the streaming data coming from out of distribution, and we want to change the model, fine-tune the model during the training, during the testing, not during the training at all, and to adapt it to the new data. So we don't want to change the loss function during the training. For example, we don't want to define an auxiliary function for an auxiliary loss for a training to use the same loss during the test. We just want to fine-tune the model during the deployment, during the test, without changing the loss function of the during training. Do we have methods for doing this?
Let me make sure I understand your question correctly. So you are saying that for the algorithm I have presented so far, I assume the meta training stage, the loss you use in the inner loop is also the loss you use during testing for adaptation. You're asking how about during testing, I have a new, like I don't know what loss I'm going to use during testing. Is that what you're asking?
Yeah.
Is that correct? Right now, no, because let's see. So yeah, because right now we are assuming that you roughly know what you are going to do during testing. Then during the offline training stage, we sort of we learn the model so that it's ready to perform what you are going to perform during testing. So that's the whole philosophy. Let's see. So
for example, there are some methods that, for example, use some loss functions such as On Turkey, for example, they want to increase the confidence of the system.
Right.
And they say if you increase the confidence of the, for example, classification task, then the model is less prone to.
Right. I got your point. Okay. So, but I think to me the limitation of that is that's assumption. Okay. So basically, you will see, in fact you will see a lot of test time adaptation paper. They say, oh, I'm going to use the entropy as the loss that I'm going to use to do adaptation during testing. I assume if I somehow minimize or maximize the entropy, my model will perform better. But again, this is assumption. There is no guarantee this assumption is true. Okay. But I think the advantage of learning this whole thing is that you are not basing on any assumption anymore, because I have a true supervision during the method training. I know I'm not making any arbitrary human design assumption anymore. So
so I think my question is related to that. So I think the concept of the inner loop and learning how to learn is really critical and really a great idea. But there remain maybe problems because, as we were discussing at test time, you kind of have this metaparameter where you have to decide when to stop adapting. So I'm wondering, first of all, if you can sort of analyze the capacity of the manifold somehow to decide how many possible options there are. Like what is the dimensionality of the adaptation space? Or like in the category example, you can analyze the within category variance and analyze the capacity of the manifold, and you can kind of decide how many new categories should there be.
Okay.
That kind of thing. Are people working on that?
Right.
Can you combine that with what you're doing?
Right. So let me first answer the first part of your question. So you are talking about for example, during the adaptation, we choose this hyperparameter by 1 to 5 gradient update.
Yeah.
So that's something that right now is a hyperparameter you have to choose.
Yeah.
But in theory, I don't see any reason why that cannot be something to be meta-learned. So you can imagine during the meta-learning, this kind of how many iterations, it could be something else that you actually learn. Yeah. But it's just from a technical point of view, it's a little bit complicated to set up this learning, how this whole thing is going to work. But in theory, this number of steps could be part of your meta-learned knowledge.
But I guess I'm also trying to connect it to sort of a more explainable way of analyzing. Like it may not be the case that the adaptation space fills the capacity of the latent manifold or whatever, but maybe there's some opportunity to look at that, or just by knowing, each category, whether it's within domain variation seen, or whether it's like within category variation, knowing that covariance, could that be a guiding principle? You're sort of treating this as completely data-driven, just with losses, but I think there's opportunity to.
Right. So I think my philosophy is I'm always a little bit suspicious about whatever human intuition we build into the algorithm. So that's in some sense I agree with Rich Sutton. So the more prior we build in, it seems like in the long run it's actually a bad thing. Yeah. So I would rather just give
But that's sort of assuming infinite computation. So I think more inductive priors. That's how you motivate it.
Right. Yeah. So the way I like to approach this is that I think in the short term I don't mind adding this kind of inductive prior. So, but for example, how to you could add 10 different inductive prior, but how to combine them, that's something I want to learn, because let's say you have 10 different prior. Maybe in this particular situation, you want to focus on this prior, or maybe they should have somehow different weight or something like that. So that is something that I think should be learned. Then there should be an upper level sort of supervision signal on how to combine them together. Yeah, for example, the first work I mentioned for the point cloud registration, those 3 different semi-supervised laws, in some sense, they are inductive prior, because those are self-supervised laws that we design. But we also have this kind of learnable parameter on top of them to learn that relative weight, and we have an upper level sort of supervision that are purely sort of it's a sort of labeled supervision. So it's not just the prior anymore. It's actually the true sort of loss function that we use for that task.
So what about catastrophic forgetting? Does it make catastrophic forgetting for example, fine-tuning the model to the new domain or new task?
Okay. Yeah, so I think this term catastrophic. To be honest, I never really fully understand why people are so afraid of catastrophic forgetting. Because for many situations, like I don't know, like for example, if I'm just using the home robot case, like the home robot might be trained on data from other people's home, but after it's deployed to my home, I want the model to adapt to my home. If it forget knowledge of how to do things in other people's home, why would I care? So in some sense, like as long as you can do well on your current situation, this catastrophic forgetting to me is not it's not something that we should put too much focus on, to be honest. Of course, you don't want to completely forget some important knowledge. Like if you are running into some situation that require you to recall some new knowledge or somehow synthesize those new knowledge, of course, you don't want to forget that part. But forget something, because I think even for human, we forget things all the time. So like you probably cannot remember a lot of the detail that happened days before. Okay, so we forget things maybe that are not important to our current situation. But we somehow sort of keep abstract knowledge in our mind, so that if we need to recall some certain piece of knowledge, we know like where to recall it or how to synthesize it. Okay? So I think this catastrophic forgetting has to be sort of grounded in a more specific scenario. Like it's not So depending on application, maybe in some cases you actually want to forget things. Okay.
Well, I think what I'm saying is there's different types of networks are more or less subjected to catastrophic learning.
Yep.
Right? So transformers seem to have more capacity to both retain specialization, but also to generalize in terms of compositionality.
Yep.
So maybe that's, but maybe also you just haven't stressed your models enough, right? With many different domain shifts or whatever.
Right. Yeah, because right now we haven't really stressed the model of learning, for example, in the continual learning in the very long run, right? So we only just have a few steps. So if you have to keep the model running for months, I would imagine that you have to do something clever. So yeah.
I really liked your introduction where you compared, I guess, individual learning to species learning, phylogenetic learning. So, but we often as educators we talk about learning to learn, right?
Yeah.
Do you have any comment on that? Like I think.
Yeah, exactly. So in fact, one of the example I didn't use it today, but one of the example I'm motivating this whole meta learning idea is precisely this kind of like a learning to learn paradigm. So the way I think about this is the traditional learning is like a training student in the vocational school. So you know exactly what you are going to do after you graduate. So you train your student to do exactly that thing. That's what the supervised learning is. So the meta learning is like a training student in the university environment. So when the student graduates, they actually don't know exactly what they will do, and the technology might change in the future when they graduate. Okay, so whatever they learn in the university will be obsolete anyway. So what you are getting is actually this capability of learning new knowledge or adapting to a new environment and adapting to a new job situation. The end result of the university learning is not a specific model or specific task solving technique.
Okay, push this a little further. So you gave examples of adapting to domain shift and adapting to new categories. How far do you think you can take your approach? So suppose I want to learn how to do new tasks, realize that, there's a new task here that would be useful.
Right.
Do you think that that's sort of going toward AGI? Do you think
Right.
there's opportunity there?
Right. So yeah. So one thing I'm very interested in nowadays. I think this is something that a lot of people in the field are interested in, are this kind of agent idea. So basically, not just adapting by parameter update, but adapting by, like, for example, if you are given some tools, then how do you sort of quickly implement or quickly sort of learn how to use the new tool. So that's something that I'm looking into hopefully soon. So basically, the adaptation involves some like new tools or new sort of or maybe other agent. So how do you adapt to them? So that's something I'm hopefully starting at some point. But as I said, so one of the slides I mentioned that even for human learning, there is we are in some sense we are limited by our genes. There are certain things that we just cannot do. Okay, so no matter how hard you try, I think it's the same for machine. So I wouldn't expect the machine if you just give it whatever, no matter what the learning algorithm is, if you just give it something completely random, completely far from what it has seen, I think there is a limit on adapting to something completely normal. Okay, so. I think there is a limit. So yeah, depending on even for human intelligence, people in AI often talk about how adaptable humans are, but I think even for human we also have limit. The flying example is the one. Another example I can give is I'm not sure if you have read this novel called Three Bodies. So there is another universe that has three suns. So the environment is completely different. I'm sure if we put us in that planet, we will not be able to adapt because because we are reaching of the capability of what nature gave us. Okay, so basically, if we want to survive in that alternative planet, we have to rely on, for example, those three-bodied nature creature living on that planet. Through evolution, they have developed this capability of dehydration or conserve themselves through that very magic technique, which is something that we don't have. Okay, so I think no matter what we do, we always have to. There is always a limit. It's just a matter of how far we push that limit. Yeah, go ahead.
So yeah, I just have a slightly controversial opinion. I just want to get your thoughts on. So you're basically using, I would say, more traditional kind of machine learning model to do this kind of object detection and characterization, right? But on the other hand, the other approach is using this kind of multimodality of this LLM because they have the text and they have the image, then they can reason with this. So for example, I would envision, let's say, if they really get the DeepSeek R1 working on image recognition, then they will have this very long chain of thought saying, oh, this may be this may be that, or is that what I'm thinking about, right? And so on. Wouldn't that actually be better ways to do this whole thing instead of kind of building from the ground up, getting the labels and so on, and getting auxiliary tasks, instead of the other way around, is you get a bigger model and then distilling to these kind of many smaller tasks.
Right. So in terms of multimodality, we do have projects that are sort of if by multimodality you mean combining visual and textual data, we do have that. So all the things I've talked about today can also be used in this kind of a multimodality model.
Yeah, but I'm just thinking, once you have the text combined with the image, wouldn't that actually help you to do better jobs to do image recognition, rather than just a simple image and then the label?
Right. Of course. Nowadays, because the LLM is a very new thing, so the work I present actually happened before the whole LLM trend. Okay, but of course nowadays we are also looking into how to use the LLM as a part, because it's a very useful tool for us as well. So how to use that as a tool to help us to solve all kinds of applications. Yeah.
So do you think about risk? So we, for many years, have admitted that one of the big limitations of the models is that they're clamped at inference time. They don't have the human adaptability. But there's also a little bit of a security blanket because we kind of know what they're going to do, right? But now if we unleash these adaptive models, they are changing over time.
Right.
And this is kind of, if you talk to the press about this, they'll say, well, that sounds a little scary.
Okay. Right. I think there are 2 points to this risk problems. There's something that I often started to think about nowadays. So here is how I think about this problem. So whenever, in the press, whenever people talk about the AI risk, I found that the risk is always associated with models that are super powerful, like LLM. When we think about, for example, image classification, usually people don't think about the risk. So if you have a model that are very specialized to something very specific, usually there is not too much risk. So a lot of risks actually come from the model like LLM that are just too powerful. They are doing things that you cannot really imagine. Okay, so there are a lot of blind spots to humans. So this is also sort of ties to this argument between specialization versus generalization. If you have a specialized thing, usually we treat it as a tool. If we treat it as a tool, typically we don't think too much of the risk. So that's, in my opinion, if we have a way so that we adapt the model to serve a specific purpose, in fact, that's actually a good way of reducing the risk because we know the model can do this thing, this one thing well. It doesn't try to do other things that are potentially risky. I think that if we deploy the very powerful and big model that release the tool, that's actually have a higher chance of risk to me, in my opinion.
Yeah, it's an interesting model of the world where we might have these very large foundation models that remain in the cloud, but they're just used to teach small models.
Yeah, exactly. Yeah.